Sorry about that.
No, not a problem. Good evening, everybody. My name is Chris Brockly-Blatt. I'm, as Simon has said, I'm the chair of the Southeast of the IMechE, but as my day job, I'm Senior Project Manager at Mullard Space Science Laboratory. And what I'm going to talk to you tonight is a bit about Mullard Space Science Laboratory and then talk about the Sun and why we wanted to go there and the solar orbiter, the mission, a bit about the spacecraft, because I'm really passionate about this spacecraft. It was built in the UK and proves that the UK is one of the best space engineers there is in the world. And talk about the Solar Wind Analyser, which I had the honour of being the project manager and the lead for the last 14 years. And then at the end, like the Chaz and Simon says, we'll answer any questions. So Mullard Space Science Laboratory is the Department of Space and Climate Physics for the University College London. I've been there since 2001. I'm almost part of the furniture. And it was formally opened in 1967. It's in a beautiful house in just south of Dorking. It's a picture of us there. I mean, we're very lucky to be. And yes, there is a swimming pool in the grounds. And for the past sort of 50, 60 years, we've entertained a lot of TV people to actually come with a lot of Sky at Night comes and films from us quite regularly, and we've collaborated on all the major space agencies, ESA and NASA being the two most, JAXA and it's a Japanese space agency, CSA, China, Russia, India, Canada, and lots of other space agencies across the world. Of course, the UK Space Agency being our main sponsor. On the picture on the right there is one of our oldest projects, the Skylark. That's one of some of our scientists started in the 60s, and we've actually got one of the few surviving Skylarks actually in our reception. Yeah. Science Museum haven't got one, we have, so yeah. And what we do is there's about 200 people at MSSL in that grand stately home, and most of them are actual scientists. And what they're looking at is different aspects of space science, astrophysics, solar physics, plasma physics, looking at what is happening in our cosmos, whether it be locally with the planets and the solar system, or far away in deep space. And they try and identify scientific questions. And from there, they propose missions to various space agencies, to like ESA, and write proposals for how do we answer these big scientific questions. And then it comes to us. The other sort of 30% of MSSL, which is the engineers and professional services like myself, who provide design, build and fly hardware. So back in 2007, I was sort of asked to lead the proposal for putting a solar wind analyzer system on solar orbiter and flying. So this is basically what I was going to try and tell the story of that. Once though we designed it, we've built it, tested it, and we actually launch it, it then goes to the instrument operation, which is the phase that a solar orbiter is at the moment. Is they're on the cruise phase to get into the scientific period, but at the moment they are actually bringing operation and analysis down, and it's actually quite fortuitous because today they've actually started. ESA have released, if you look on Twitter, ESA have released a lot of papers on the first sightings of the Sun made by solar orbiter, and then from there that data is analysed from development models, trying to verify how we understand the Sun, how we understand those bits of astrophysics, and then that leads to more questions, which then leads to more missions. So I'm already working on the next mission for solar physics, but I might talk about that later. So some facts. Well, the Sun is really far away. It's about 150 million kilometres from the Earth. It's about 330,000 times the mass of the Earth, and it makes up almost the whole of the mass of the solar system. About most of the other 0.2% of the solar system is actually Jupiter, to put it into context. Now, the temperature of the surface is about 5,500 degrees C, and the actual corona, the atmosphere, the fleecy bit, is actually sort of 1,000,000 degrees C. And we don't know why that is, why you got this discrepancy. And they're trying to understand that with some of the papers that are coming out today. So some of the breakthroughs at MSSL, and I'll show you some pictures hopefully at the end. So what's our fascination been with the sun? Now, I'm going to stress here that I'm not a solar scientist. This has been what I've picked up about solar science is basically 14 years of sitting next to my solar scientist and listening to him, and it's like asking questions. So I will try and do my best by why the sun fascinates us. But if you do have any solar physics questions, I can actually go and ask them and get back to you at a later date. Galileo, sort of the 1600s, was invented the telescope, started studying the sun, and he saw these dark spots. We know these are sunspots. And so there are the website there actually shows some of the Galileo project has actually documented all his drawings, which this is one of sort of counting sunspots from there. And all the way through, we have sort of monitored sunspots come and go, but the amount is repeatable. And there's a sort of like 11-year cycle where we go from what we call a solar minimum, where there's minimal sunspots, up until a maximum, which is a really majority the surface is covered. And actually, yeah, today when we look at the sun, we use a telescope to look at the sun. Now, I don't advise you that when you're at home, do not look at the sun through a telescope. These are special adapted solar telescopes, or pinhole cameras. You could use that. It's actually quite boring when we look at it in the optical, and when we start looking at different wavelengths, so this is shorter the UV wavelength, the sun actually becomes a very violent place and very interesting. And a lot of these white patches in this thing where we've got lots of loops coming through actually relate to these sunspots. So the sunspots have fascinated solar scientists. So what sort of mechanism forms them? What sort of, what else do they cause? And the magnetic structure of the corona is these sunspots actually are sort of basis for these loops. This is plasma escaping from the surface of the sun and then following the magnetic field. So you've got a north and the south bar magnet pole on it, and it can be actually quite dynamic because the plasma is trapped in these loops. So that's a picture there from an ultraviolet emission. Some of these sort of big plasma loops actually are huge, and if you put the scale, the Earth to scale of these, it would kind of swarms. And some of them actually, the plasma escapes, sort of has so much energy it actually escapes from the surface of the sun. And a lot of this is called, we're now understanding as space weather. And this space weather, this escaping plasma, can affect the whole of the solar system. What protects us is our magnetic field, and some of our atmosphere. And of course, when these particles hit our atmosphere, it forms the energy is given off as light, and that's when you get your aurora borealis, your northern lights. So a lot of this act like a superhero shield to protect us from the majority of the solar wind. So if we see some of the eruptions, some solar flares and coronal mass ejections, as this plasma is sort of escaping from the sun in the centre, sort of the dot in the centre. These are the reason why this picture is bitty. It's been taken from different satellites at different ranges, and what we wanted to do with Solar Orbiter is try and get a picture of all together as best we could of more of, so that you see not the whole big picture of the sun and the surrounding bits around it. But you can see these big explosions or eruptions of particles from the sun sort of are very, very violent, very turbulent near the sun. And really, up until Solar Orbiter, we didn't have any spacecraft that actually went any closer. And so we were sitting outbound where the Earth is on this line on both sides to actually observe this. So the idea was to put Solar Orbiter as close as we could get it to try and experience these turbulence of plasma a lot more. Right, so that's on to Solar Orbiter. So the plan was to get closer to the sun than any current mission. Most missions were the same, what we call the same AU or the same radius away from the sun as the Earth is. So the idea was to try and get the spacecraft closer to the sun and to make increasing high solar latitudes as well. Up until now, all our solar satellites have always been in the equator. So the mission was designed to use gravitational assist by using the planets their gravities to assist to do slingshots around the planet. I know it sounds very Star Trek, but we do use it to actually get us into higher latitude, because we've never seen what's at the pole, what's happening at the pole itself. And the other special thing about Solar Orbiter is we carry two different types of instruments. We have what we call in situ and remote sensing. Now, the remote sensing are telescopes. They are taking pictures at the sun in different wavelengths to get a pictures. Like I said, you've got a picture of the optical and compare it to the very violent picture of the ultraviolet. We've got those cameras on board, but at the same time we've got detectors that will measure properties at the spacecraft, so that it can measure the emissions off the sun. And we're trying to get that link between what's happening on the sun and actually what the sun is giving out in its times of space weather. So a bit more into the spacecraft itself. It's 1.8 metric tons. So it's about the weight of a Ford Focus. Its body is, when it's all folded up, it's sat in the top of the rocket, but when it's all laid out, you've got 18 meters from end to end of solar arrays, and then the boom that sits at the back is down here, is about 4.4 meters, and one of my sensors actually sits at the back here. It had the antenna, the three spiky bits are actually one of the instruments. That's the radio and plasma wave antenna. They're measuring the radio waves coming off the sun. Again, that's an in situ sensor. And the dish at the bottom is our high gain antenna. That's the dish that sends back the data back to the Earth. It's designed to be autonomous for about 80 days when it's when the sun is between us and the Earth. So there was a lot of designing in the mission itself to actually say, right, how can it think for itself? What will happen during those 80 days? And can it actually look after itself? Do we have enough memory on board to store that much data for 80 days? So the list of instruments there's 10 instruments. The in situ ones are, remember this, EPD and the magnetometer, the RPW and SWA. So there's 4 in situ ones. So they're measuring properties of the spacecraft, of the radio waves, of the magnetic field, and the particles that are moving past. and the rest, EY, METIS, FI, Solar High and SPICE are all different cameras at different wavelengths, measuring, taking pictures of the sun. Sorry, that's my little doorbell. Each of the instruments was put together by a consortium of scientific institutions, and because no one country can afford to make one instrument, so there were sort of lots of teams spread out across the globe working together, with lots of different leads. We had an instrument from Spain, one from Belgium, one from Italy, two from the UK, one from Germany, and two from the US, one from France, one from Switzerland. My particular instrument is the one at the bottom, which is the Solar Wind Plasma Analyser, and that's led by my Professor Chris Owen. He's my chief scientist, and I'm his project manager. So the way it works is, if you liken, Star Trek, I love Star Trek analogies. If you liken it to the Enterprise, Chris is Captain Picard and I'm Commander Riker. I run the day-to-day operations of the project as we were building it. Okay. So I was going to show you a quick video. This is a video from ESA showing the mission, the journey to the sun. And Solar Orbiter leaves the Earth. It's heading out into the solar system, and then it uses, like last December, it used Venus to change its trajectory very well, and it keeps, as it flies past Venus, next flyby is August this year, to change its trajectory to it actually goes into the inner circle, inner space around the sun, and then it starts in November this year. Earth will change it again, and then it will start its proper scientific observations. It will go as close as point of a third of the distance between the Earth and the sun, or a third of AU, which is about 50 million kilometres, and then it will come out as far as 1.5 AU. So as it's going round, and then it will do, it's something like 20 or 30 laps, and we're looking at possible 2027 mission end. But we will keep going, as all of this. It will keep, as it uses fuel to adjust slightly, but it's using the gravity assist to really change the direction, its trajectory. Oh, sorry, that was fine. Okay. Good. There we go. Going to mission end. Yeah. 2027 is when the first mission, and then we get the extended mission. After that, I don't know. Perhaps most of these type missions are actually try and fly them into the sun. So this is a photo of Solar Orbiter itself. Now I'm going to talk about the Solar Wind Analyser, of which it's made up of 3 sensors. First one is HIS, that sits at the front. That's the heavy ion sensor, and that was built by my team in the States from Southwest Research and University of Michigan and University of New Hampshire, with help from Goddard. And then underneath that, on the bottom of the heat shield, is what we call SWA PAS, which is my proton alpha sensor. So HIS measures sort of low mass molecules, and it also measures their speed, while PAS actually measures the energy of proton and alpha particles. And then at the back, We've got EAS, which actually is built by MSSL. One of its with the detectors from Paris. That is the Electron Analyzer System, or EAS, and that sits at the back at the end of this boom, trying to be as away from the spacecraft as possible to try and catch electrons from the sun. Now, all these three sensors were then connected up to a onboard computer or data processing unit, the DPU, which was provided by a group of companies in Italy, and they're all connected with lots and lots of meters of harness. Solar Orbiter itself is about 2 meters by 2 meters, sort of like this washing machine, and again 18 meters of solar panels. It was built at Airbus Stevenage in just north of London, so completely wonderfully British spacecraft. The heat shield at the front was specially designed, and that's taken the longest time to develop because it's looking at sort of spacecraft temperatures, surface temperatures of 500 degrees C, and it always points, unless it's when it's past the Earth it doesn't, but within Earth's sort of orbit or less, it actually the spacecraft always points the heat shield to the sun, because we're looking at 500 degrees C, and all electronics, no matter where you are, always likes to be room temperature. So we're trying to get our or electronics to room temperature. Now, the problem we had with SWA is we had two sensors. We had our proton sensor and our heavy ion sensor pointing out over the heat shield, and they were getting really hot, and we had to have radiators and look at the considerations. Meanwhile, our electron sensor was sitting at the back, and as you can see, it's in the almost black. It was freezing, and so we had to design a thermal regime to keep that warm. And we only had about 12 watts of power to actually try and keep it warm. As power, it was on this phone was very much a commodity, sought after commodity. You had the solar panels, and of course when they're close to the sun, they have to throttle back. They can't be sort of full on, or they get too hot. So we're always scavenging ourselves for power. Okay, so yeah, as I said, we've got the three sensors: EAS, HIS, and PAS. We've got different, all connected up to our DPU, various contingencies. So I was not only looking at the team in the UK building the EAS, but I was also responsible. I had project managers and teams reporting to me from America, France, and Italy, and that got interesting for some teams, because I didn't realise, being a sort of London girl, how, when I first got on this project, how different cultures integrate with business. So the Americans wanted to start their meetings early. The Italians wanted to start, sort of 10 o'clock and have 2 hours for lunch. And the French, wanted to work late into the evening. So we actually got on very well. We actually formed a family, which we're still all in contact with. And we do enjoy, still talking and friendships over it for the last 14 years. All right, so I was going to go on to EAS and a bit about the technology of how an electron analyzer system works, and how we went about building it. Now, with what we were trying to do, we're trying to measure electrons and trying to know which direction they're coming from, as well as their how much energy they have, and we attract them into our detector by a set of plates. So we've got high voltage, positively charged plates, and they alter the course of the electron to actually curve round and hit our detector. And we use what we call a multi-channel plate, an MCP, and that amplifies the signal down to the anode, and then the anode says, oh, I've been hit by an electron coming from this direction, and I've got this much energy. And from there, they can build up a picture of how the energy profile of the solar wind. And from there, there's different types of solar wind that they can identify. And from that, that gives a bit of a clue to actually what caused the solar wind. And this is our design. This is, on the left is our CAD design. EAS itself is actually 2 instruments. We've got 2 of these electron instruments. They've got 3. They can receive an electron from 360 degrees all the way around. These are the bottom right hand corner. You can see the bulb, the 2 bulbs. If I go back a bit, the green curves you can see on the picture on the bottom right is those golden bulbs, one above the other, and they're highly positively charged to drag in the electron, and then it goes down to, if you take the mesh and those curves off, what you see underneath is that top right picture of the anode and the detector, and that's split into little segments, so we can actually work out which identify which segment it hits. And these 2 heads sit on the box, and each one is independent of the other. And the reason we got 2 is because, one, there are certain angles that are going to be blocked by spacecraft, or they're going to be blocked by the box itself, or these spokes that hold the top assembly together. And so you've got 2, so you can overlap and try and not have so many missing pixels. The idea is to get a full 360 in all directions of it. There's some pixels we still lose because of the spacecraft, but that was the plan. The other plan was redundancy. If we lose one head, we've still got the other to actually do some science with. And the pink, if you look at this, the box with the 2 heads on each side, the pink below there, those are our representations of our different electronic boards, which are done. At MSSL, we've got capabilities doing full machining out the aluminium. We've got full machining out for the sort of very much where we've got a CAD/CAM system. However, a lot of this was actually done at Taunton Aerospace. Over the years, we've used a lot of sort of Formula One teams as well to get the precision that we need to form this. Now, EAS, because it's in a high radiation environment, is actually a lot of the engineering panels, and the box itself is actually 2 millimeter thick. Normally we go for 0.5 millimeter to try and cut down on weight, but and just have impressive sort of structures that are very stiff. But we had to go for 2 millimeters. Now this to us is actually, it's sort of battleship engineering in the fact this is all heavyweight stuff. But it's sort of, we are sort of try and go for lightweight structures. So what we start off with when we have from the proposal stage, we for this project, because it actually, in terms of space projects, it was actually quite short. The original plan was about 8 years that we go from start to finish. We decided to go for a one-shot design. We're going to go from our basis of previous projects, there are Cassini and Cluster, which is like father and grandfather of EAS. We decided, right, let's go and design EAS from the start as a flight program, and from there we went into try and get that model. That model hasn't really changed over the years. That CAD model, there's been tweaks here and there when we looked at the structural or looked at the thermal, but fairly enough, it was fairly spot on. And we use that to construct our thermal models. This is normally use a program called ESATAN, which is a space specific thermal modeler. And the reason I put this picture, this is one of the early models, thermal models of EAS, and I put this one in because I actually did it. Because I was doing some of the thermal modelling, as my background was originally thermal engineering. And what we were looking at, we've got a lot of heat in the electronics boards at the back, but we didn't have where it was going to be very cold because we've got these because these open apertures to space, and because EAS is at the back and just looking at cold space, it was getting very, very cold. So we had to look at putting more heaters down where the heads were to actually keep those warm, because the MCPs, they're a glass-based material, and so they've got the CTE of glass, so they've only got a sort of very, very small temperature range that they're working. So we're trying to keep that fairly stable. We built a prototype. The first thing we do, built a prototype, saying, okay, from previous missions, we got to build it. We've got to put two together to start with. The first one was we've got to put two together. We had Cassini, we had a detector that was 360, and look angle, and we say, well, for EAS we've got to have two together. So we built a box with what we call commercial electronics, stuff that we get from RS, stuff we can get off the shelf, go to a PCB manufacturer, so a quick turnaround, to build this prototype with one head to actually prove that it would work. From there, when we put it in a chamber, fired electrons at it, so brilliantly it works. Okay, we had a design review and they said, yeah, go ahead. And that's when we start building what we call a structural thermal model, STM. That's the next model that we built. And it's basically what we're asking the question is, can we survive? Can we? So the model is, we build it as best we can that's like flight, but it doesn't operate. So a lot of the electronics boards were replaced by blocks of aluminium that mimicked the weight and the structural mass and the C of G of the actual electronics boards. And we put heaters in to mimic the power dissipation. But it doesn't actually work. You can't fire electrons at it. And then we used it to wrap it up in its thermal blanket. So this, I know it looks like a badly wrapped Christmas present you've done at Christmas Eve at 12 o'clock and you've had too much to drink, but it was our first attempt at making sure that the thermal blanket fitted. It's actually quite a thick thermal blanket, 20 layers, to try and keep the heat in with the EAS as much as possible, and at the same time trying to leave the apertures open. And we instrument it up. Underneath that blanket is lots of thermistors and heaters to try and simulate the operational, where the heat would go when it's operating. And we put that in a thermal chamber, a vacuum chamber, and mimic various stages of the mission. We then put it on a shaker to mimic the vibration, because the actual structure itself is flight-like. So we're trying to effectively prove that and correlate our structural models, see if there's any weak points. For EAS, one weak point we did have was actually there wasn't enough margin of safety on one of some of the fillets on the housing around here, so that was changed. But generally, my just got it spot on first time, so I was really pleased. And then once we finished testing and making sure, going past the qualification levels, past the levels that it would see to give us margins of safety and correlate our models, we then sent it to the spacecraft. And that's what the spacecraft did. This is Solar Orbiter STM that was built at Airbus. And this is with some of our instruments. The left picture on the left is our spacecraft. And then the top right is, that's PASS. and underneath is EAS at the end of the STM boom, and then that's put into a vacuum chamber and does thermal testing, and then put on the shaker and shaken to bits, and then get the information fed back. Now, by this point in the program, we would normally say, okay, we get this information back and we start designing. We start changing the design, but unfortunately, due to it was really compressed, we'd already been building. We were actually trying to build a flight model. We were and had finished what we call the electrical model testing. Now, whereas the STM, you're looking at the mechanicals, you're looking at the thermals, and you're looking at the structure. The electrical model looks at, does the electronics work? Does the software work? It doesn't matter what it looks like. What we're trying to do is making sure it works, and then we don't actually put it in a chamber to fire electrons at it, but we have chips on the board that send simulated signals to say, oh, I'm an electron. And what we're looking at is, can we actually get the high voltage? Can we actually get the software to talk to the sensors? Can we, and work from there? And we start off with the detector itself, which is here on the right, sorry, on the left, talking to the controller board within the electronics with an FPGA on it, and that's what we start with. We then get up to where we start adding more electronics. So this is all, the first bit is all powered by power supplies on the bench. We then get up to where we actually start putting its onboard power supplies in, and we start slowly increasing increase the complexity of the electronics. And so actually with EAS, we decided, you can have whatever box, you can put it in whatever box, but we actually built a couple of STM boxes at the same time, so we could actually have something to put EAS into. So that's why EAS looks like the EM looks like EAS. Now, I like this picture because it shows you, at the same time I was developing another program, which is my son. My son, when I started SWO, was 6 months old. And this is him about age 6 or 7, who come home for a day, sort of an inset day, come to work with mum, and he was helping one of my engineers actually do some testing. And I'm actually pleased to say he's actually taken up GCSE engineering now. So I haven't put him totally off. He's now 15, to say that's how long these programs take. So when we was doing testing EAS, that is EAS, and actually the guys we had to have covers on the end of these sensors to stop bits dropping in, and they came up with so they started to use tinfoil in the first instance, and they came up with these red tag items, which are to test the proper things that we put on the end of the sensor heads on for the flight. And this is the STM, the whole of all the 3 sensors and the DPU. So in the front part of the picture is HISS. HISS is a huge thing. It's about 10 kilos. It's about a good 70 centimetres tall. But they didn't need all that for their electrical model. They just needed the box at the base, which had all their electronics. And the same with PASS. They could get rid of the detector unit at the top and just have the box at the base. So those are the one in the foreground, HISS, and the one in the golden box in the background next to EAS is PASS, and then the black box is the DPU. And we knew that we weren't building the harness between all these boxes wasn't going to be built by us. It was going to be built by the spacecraft, because we knew it was going to be long. But we decided to build a representative flight harness anyway to test it, because we'd never really built a harness that was 14 meters long before. And so they curved it up all on the bench, and we went, we can't test like that. We can't test, it kind of shows you the distances that this harness has to go over. And so we actually came up, I haven't got a picture of it, with a smaller test harness that we actually send off. This EM setup with the 3 sensors and DPU eventually went to the spacecraft, and their EM setup to test their software. Okay. And then we got on to building the flight model, and this is EAS, some of the testing. This is the top right, left-hand corner picture is EAS in its chamber, setting up for it to be fired with an electron gun. And it's inside the box itself. You can see the most notable thing is the colour change from the very thick yellow PCBs, sort of commercial, to the flight qualified PCBs that we use. There's only a couple of manufacturers that we can use in the EU, UK and EU. So these are sort of more complicated to actually produce. These boards, we don't produce the PCBs ourselves. The boards are produced and then they're sent to MSSL, and we actually populate them. We actually hand solder or use a pick and place machine to actually populate those boards at MSSL ourselves. And you can see the wiring loom within the sensor is very complicated. One day going around, the engineers were going comparing hands, who had the smallest hands to actually get in to start making some of these connections. Going back, one of the other things we started developing, we looked at the blanket and realised some bits because it looked like a badly wrapped Christmas present, that it wasn't performing as well as it could. So we went back to the drawing board in terms of designing the thermal blanket. Our thermal blanket was produced by Rutherford Appleton Laboratories in Harwell, and we went back to start working with them to actually find something that was better tailored. So what we actually got here, we actually produced a model. A lot of it is 3D printed of a tailor's dummy. So they could actually cut out the material and lay it all up and produce a better looking thermal blanket. In the meantime, ESA also asked us to say, can we not have the shiny surface because some of the light is being reflected backwards? Could we have it as black, which is worse in some respects, is worse performing thermally, but it was actually made it a lot. This is a lot of about space engineering. A lot of it is compromise, and to get over that hurdle. So this is EAS flight model, and that's with its what we call red tag covers, so the covers over it which put on the ends to actually make sure that nothing dropped down them, and they're red because they get to warn people when they're actually at the launch pad to actually take them off. And yes, we did get them back so that we know they actually were taken off. And compared that to our STM model, I think we did a lot better job this time with the thermal blanket, a lot neater. But again, the design first time kind of worked. And then what we do with the flight is we put it through a number of tests to make sure it's accepted, that we haven't workmanship performance tests to make sure that it's working properly. So this is EAS all instrumented up in our thermal chamber. Picture on the left is our big vacuum chamber at MSSL optical chamber, and my chief engineer sneakily having a sleep while he's waiting for we got a thermal stability. We had to make sure it didn't go over a change of 4 degrees per hour. So you've got to have somebody sitting there, and it's it's always who draws the last straw to actually do that test, to sit there and watch the test. And then once we've done all the acceptance tests on each of the unit, we pulled all 3 sensors together at MSSL. So we've got EAS here with its red tag covers on next to our DPU, and in the back, the big one is HIS, so our American unit with its thermal blanket on, and the black package is our French unit. You can see all these red items here. These are all covers for their apertures to make sure that nothing gets sucked in or dropped in when they're being handled on the ground. So that was about May 2018 that they all came together, and then July 2018 the DPU went off to the spacecraft to be integrated, and the rest of the units left about October 18, and then it was sort of integrated onto the spacecraft. The spacecraft then moved to IABG in Munich, where it undergone its own vibration test. This is a picture of the flight unit sitting on its vibration test plate, ready to undergo its vibration test. Here it is on the fixture at one of the press days. We don't have small people to show this, but this is the actual show how big it sort of really is. EAS is sort of folded up on its boom on the other side. This is all sort of all folded up before the deployment. And there it is in its thermal vac chamber at IABG to do its thermal test. Okay, which all went successfully. Integrated again. And in the meantime, our Taylor's dummy, sort of in 2018 and 19, was at the Science Museum. There was a big exhibition of the sun, and I think they actually moved to Manchester. And I think they're staying there until November. At the Science Museum in Manchester, they had a big exhibition on the sun, what the sun does for us, and at the end of it is a bit on Solar Orbiter with a model. There's a bit of one of the feed throughs. There's a magnetometer, and then there's our EAS, our Taylor's dummy, and the standing next to my son, because he was, trying to look as interested as he could about his mum's work. So it's then flown over to the US. It's done all its testing in Germany. Flew from Germany straight over in October 19. Where it was integrated into the rocket, ULA services integrated into the Delta IV rocket, and on 9th of February 2020, it was rolled out onto the launch pad. Launched. This lovely picture. A lot of us were there. Actually sort of Banana Creek, which is a couple of miles away, to actually watch it. The system engineer for Solar Orbiter from the NASA side, a guy called Joe Cirillo, who I've come to know over the last 14 years, said it was the most boring rocket launch he'd ever seen because everything was green across the whole board. He said it went perfectly. A lot of these things we've all been told to expect. It might be delayed or you might have to wait a few days, but it just went straight away. It was gone. It's quite emotional. And there is a satellite, there's a website there, or you Google where is Solar Orbiter, and that tells you where, gives you with this slider gives you the path that Solar Orbiter is done. So this is sort of 15th of November last year. I should update this really to where it is now. It did its slingshot around Venus, and it will do another one in a couple of months. And then you can track where it is and where it's been and where it's going and how long it takes to actually talk back to Earth and things. So February 2020, we all watched it and said goodbye to it, all came home and got on with our other jobs. We had to wait a month. Everything deployed perfectly. We had to wait a month for all the atmosphere for it to outgas all the atmosphere within all the instruments to pour, because we can't use our high voltages in atmosphere. We have to use it in vacuum, so we had to wait for all the gases to move out all the sensors. And by that time, sort of March 2020, we were in lockdown. Now, normally when we commission instruments, we've got engineers and scientists standing at mission control, looking over the data. But of course, we couldn't do that. Our mission control for Solar Orbiter is in Munich. And our engineer is a guy called Daniel Lakey, who's actually on Twitter. It was quite funny because he wrote an article about trying to control Solar Orbiter while at home with his cat, and how much his cat actually influences the path of our spacecraft. And this is Chris Owen, this is my professor, who is sort of commissioning, getting the instruments turned on and working while in his son's nursery. So the past year they've done the first 3 months of the flight has been commissioning, and then we're into the cruise phase where we have been operating, trying to get some science and doing far away look-sees and looking at sort of on the way to the sun. And that's sort of some of the data that's been coming off on the right hand side. Sort of the initial data from HIS is in the middle, one of the EAS is at the bottom. So these maps of look angle and energy levels. So that's not quite as sort of for plasma physicists that's exciting, but for looking at some of the cameras, some of the first light pictures that we got in June last year from the E1 FI instruments, looking at the sun in so much detail that this is what they get in all exciting. What the papers today have been released is because we've never been able to zoom into the sun with such detail. They're seeing these little white spots, these campfires they've nicknamed them. Perhaps that's giving us a clue to why the sun's atmosphere, its corona, is a lot hotter than its surface. So that's sort of the first light pictures. So I know I've gone over my time, Simon, sorry, because I could talk forever on this. So hopefully I've shown a bit about how it's a dynamic environment, and how Solar Orbiter is going to address this, and gone over about how I had pleasure leading this team for the last 14 years, a large consortium to provide sensors. So as the people I'd like to thank are my scientists, and also sort of Lucy and Daniel and Yanis, who are scientists at ESA, my payload engineer and Pat Cross. So